Okay, yeah, thank you all for being here. We want to get started with our first speaker. Uh, uh, so our first speaker is Scott Aaronson. I'm sure all of you know him, but I'll still say things about him so that you know what to focus on. Scott is a professor of computer science at UT Austin. He's also the founder and director of Quantum Information Center there. Many of you might know of his amazing works in quantum computing and quantum information. He's also, perhaps even better known as a wonderful expositor, for which he recently won the inaugural Trevisan Exposition Award, a very well-deserved honor. Through his blog, he has thought about various things related to science and beyond. In particular, the effect of AI, how it affects us, whether we are nearing a singularity, and so on. He's also worked on concrete questions related to the work, related to the effect of AI, like watermarking and how we might do it. I don't want to list all of his awards. There are too many, and it would eat into his time. So instead, without further ado, we are very excited. Scott, please take it away.
Okay, thank you so much for including me in this as a sort of mere recent dabbler and moonlighter in AI. It's great to be here. How many of you remember Microsoft Clippy, by the way? We were just, okay, good, that's most of you. I was just talking to John Kleinberg about it. We were wondering whether this is like only old people remember it. But I sort of screwed myself by, sending Pritish this title, right? Which then sort of committed me to, people are going to expect me to answer this question, and I'm not sure if I will. But let me just sort of say a few things. So like this is a graph that I think Ray Kurzweil maybe 15 or 20 years ago explaining why he predicted that machines were going to become intelligent within not in millennia or centuries, but in just a couple of decades. And we were going to actually be faced with what Alan Turing wrote about in that famous article. Okay, and he said, you just have to look at scaling, right? You just have to look at, how many flops can you do per second, per dollar. It's on an exponential trajectory. And, he said around, the 2020s, that starts to cross estimates for the computing power of the human brain. And, I remember seeing that argument. I remember thinking, that is like, the one of the sloppiest, dumbest arguments I've ever heard, right? We have no idea how many sort of secrets of organization of the brain will need to be discovered before we can actually replicate what it does. So now here we are. And I think that, rather than inventing sort of elaborate excuses, we should just acknowledge that, the sort of very simplistic scaling hypothesis basically turned out to be right. Okay, and you've all seen sort of what that has led to. Very famously, just a month ago, we have seen arguably sort of the first major open mathematical problem solved entirely by an AI model. This was the unit distance conjecture, which Paul Erdős put forward in 1946. Okay, and so his conjecture was that if you're given n points in the Euclidean plane, then you can have at most n to the 1 plus little o of 1 pairs of points that are unit distance apart. Okay, and the best construction that he could think of was just a square grid of points. Sort of, appropriately scaled. And he analyzed, how many unit distance pairs that could have. He conjectured that that was about optimal, and that conjecture stood for, 80 years, okay, until last month, when an internal OpenAI model refuted this conjecture. Actually, it was my former undergrad working with me, Li Ji Chen, who fed it the prompt and literally just prompted it to prove or disprove this conjecture. And it spit out a disproof, a counterexample, which turned out to be correct. Okay, and its counterexample used results that were known in algebraic number theory, that were known to certain experts in that field, but that would not have been known to almost anyone who had, thought about combinatorial geometry. But of course, a GPT knew these results, because why wouldn't it? And using that, it was able to construct by sort of projecting from a certain lattice, a set of points with n to the 1 plus delta unit distance pairs, where actually it didn't even bother to work out delta, but humans then worked out that delta was 10 to the minus 38. Okay, and then some humans quickly managed to improve that. Okay, apparently Will Sawin had thought in this direction before, and so within a few days was able to improve that delta to 0.01, and then it was improved on Math Overflow to 0.035. We know that it can be at most 1/3. Okay, so that's where things stand now. This has led to, already within the last month, led to other developments in pure math. So I heard about this about an hour, after it, Timothy Gowers, I guess, posted it on Twitter. I heard about it when, I was sitting in my office at UT, and some of the grad students came to me and told me, they said, "Did you see this thing about unit distance?" I said, "What thing?" And let me show you a picture of how those students looked. Okay. So, it seemed only appropriate to me that I should have AI generate the picture as well. Okay, and this is it's a good picture, isn't it? This is really what it looked like. The students were despondent. Okay, they were. Wondering what does this mean basically for our future? Our sort of what does this mean for the whole sort of human enterprise that we are embarking on, right? And I think frankly it's easy for people who already have tenure, who are already kind of on the downslope of their careers, like me, to say, oh, this is cool. This is we're going to answer so many questions. Let's just see what this leads to. But from the perspective of someone who's just embarking on their career, I mean, of course, they're worried about it, and so I think that we should sort of confront that honestly and think about it. But so I of course I posted something about this on my blog. And then I was actually very surprised. I didn't expect the kind of reaction that it would get. The sort of the main reaction, although with hindsight I should have, the main reaction that I got from my commenters was sort of contemptuous denial of what had happened. So let me just sort of paraphrase what the commenters on my blog wrote about this unit distance, disproof. You can go read it if you want to see more. But this is just yet more marketing hype from the AI companies. No, an AI did not prove or disprove anything. It just generated a whole bunch of slop, and then humans staring at that slop managed to extract a proof. And then this was my favorite. Okay, this unit distance problem was not real math anyway. It's just Hungarian combinatorics. Okay, no surprise that AI can do such trivialities. Wake me up when it can do real math like Grothendieck type algebraic geometry. Okay, and then, when questioned about this, they made it explicit. Timothy Gowers, a Fields medalist, and all the others who were praising this, Noga Alan, these are not real mathematicians. Okay, Erdős himself was not a real mathematician either. Okay, so they have been judged by like anonymous, commenter 473 on my blog. Okay, this is, it's like. I'm very honored to have won this Trevisan Prize, but like it did not come without blood or sweat or tears, right? This is what I deal with every day. Okay, so I was thinking about this reaction, right, and in response, I actually showed my blog readers a recent social experiment that was done, which I now consider maybe one of the great social experiments of all time. Okay, and it was someone on Twitter posted this picture. Okay, they said, I used an AI model to generate this painting in the style of Monet. And then they simply said, please describe in as much detail as possible what makes this inferior to a real Monet painting. Okay, and they got sort of a bounty of detailed responses, which I've quoted some of them here. Okay, wouldn't hold up to the real thing. There's harshness, no soft blending of colors, no depth, no symbiosis of elements, no frame, no sense of threshold between subject and object. Looks like high school level 101 artwork. No cohesion of elements, it's garbage. It's emotionless. There's a spark missing. It's not Monet, it's an undergrad art student study. No tranquility. Water seems like it's on fire. It's busy, artificial. One wants to jump from the water and get far away from the place the AI crafted. Purple on the lily pads is inconsistent. Brushwork is bad. All adds up to make it look like a trained but untalented student's attempt. You can probably guess where this is going. The person then revealed that this is a real Monet. Okay? So, there's clearly sort of a huge psychological element. There's a huge element of cope. And I think that, as Timothy Gowers pointed out, others pointed out, clearly, like if a human had disproved the unit distance conjecture via that proof, they probably would have been published in the, annals of mathematics, and, it could have gotten them tenure at just about any math department, right? So, so I do think that we have to try to look at the thing, as it is, not sort of invent clever excuses for it. But what is AI actually capable of? So, of course, I've been experimenting with this, as probably most of you have been as well. So, what I wanted to do in the next part of the talk is just give a few case studies from my own work of what I've been able to do and not do with the help of AI. So the main places where I have used AI to help me are in the sort of compared to AI old-fashioned, slow-moving, and traditional field of quantum computing. So here are the dramatis personae, right? We'll just be talking about some of these basic complexity classes, which I mentioned in my talk on Tuesday that physicists have much better names for things than we have, like quark and gluon. We're stuck with QCMA and BQP and PP. Okay, but so we'll be interested in sort of these complexity classes. I'll define them where it's relevant. And so there was a particular, not the biggest problem in quantum computing, but a little problem that's been around for decades, and that I'm kind of curious about. And it's the question of whether the class QMA has perfect completeness or not. Okay, so let's just remember what is QMA. It's quantum Merlin-Arthur. Okay, so it's the quantum version of MA, or if you like, the quantum version of NP. Okay, so it's defined as the class of languages L for which there is a polynomial time quantum verifier V, so that for all inputs X, if X is in the language, if the answer is yes, then there is a polynomial size quantum witness state, psi, such that V accepts X and psi with probability at least 2/3. If X is not in L, then for all attempted witnesses psi, V rejects it with probability at least 2/3. Okay, so you see these probabilities, 2/3 and 1/3, and those are there for just the usual reason why they're there in complexity theory. That, if you don't like them, you can always repeat a bunch of times and you can amplify. In this case, actually, to amplify in the obvious way requires many independent copies of the state. Okay, but then Arthur can just ask Merlin to give him that. And so you can clearly amplify to exponentially small completeness and soundness errors. Okay, but then we can also define a subclass of QMA, which is called QMA1. Okay, and this is the same, except that if X is in L, then you always have to accept. Okay, so you have to accept a valid proof with probability 1. So I should warn you, this class is a little bit ill-defined because, normally we say that like the specific choice of gates that you use in defining your quantum complexity class doesn't matter that much because, with one set of gates, you can simulate another set of gates up to an exponentially small error. Right? But here, if we're requiring 0 error, then the specific choice of gates could actually matter. Okay, but for any given reasonable choice of gates, we can define this class QMA1. Okay, the issue won't really matter for us in this talk. And then there is the question of does that equal QMA? Okay, so clearly it's contained in QMA. Long-standing open question has been whether it's strict. And so what I should remind you is that for classical MA, one of the early things that people discovered in the 1980s is that MA does equal MA1. Okay, so the proof of it is actually like similar to how you show that BPP is in the polynomial hierarchy, for example. You could use hash functions. Okay, but we do know this for classical MA. It was also shown in 2011 that if you have QCMA, which is sort of quantum classical Merlin-Arthur. So that's the hybrid version where Merlin has to send a classical witness, but then Arthur can verify it using a quantum computation. Okay, so for that version, we again have perfect completeness. Okay, that's a non-trivial result, but that is known. Okay, and so it seems like a reasonable conjecture that maybe QMA could also have perfect completeness. Okay, but in 2009, I showed an obstruction to that. Okay, namely, I showed that there exists a quantum oracle, U, relative to which QMA is not equal to QMA1. So the quantum oracle was a notion that Greg Kuperberg and I had actually just introduced a couple years prior to that. Okay, when we realized that if you want to separate certain like pairs of quantum complexity classes relative to an oracle, it would be much easier to do that if you allowed the oracle to itself be quantum. Okay, what do I mean by that? I mean the oracle is some unitary transformation that you're allowed to apply in a black box fashion, right? So it doesn't necessarily correspond to any Boolean function, like mapping a classical input to a classical output, right? The oracle is just you apply this unitary, on these n qubits. Okay, and so we were able to show, Kuperberg and I, for example, were able to show in 2007 that there is a quantum oracle that separates QMA from QCMA. Okay, and the problem of separating QMA from QCMA by a classical oracle actually remained open until just this year, when it was solved, and that was one of the highlighted talks at this year's STOC. Okay, which I'm very excited about. But you can see that the classical oracle separation was a lot harder. Okay, so likewise, for QMA versus QMA1, I was able to separate them by a quantum oracle, even if not by a classical oracle. So how did I do that? Well, the oracle that I needed was just acting on a single qubit. Okay, so all I need is a black box rotation that takes a single qubit and that rotates it by an angle theta that, let's say, is either 0 in the no case, or else like it belongs to some interval, like let's say between half a radian and 1 radian in the yes case. Okay, and then we say, okay, so certainly, a quantum computer that is allowed bounded error can easily decide which of those two cases we're in by querying that oracle a few times, right? This task is in QMA to the U and even in BQP to the U. Okay, but is it in QMA1 to the U? Okay, well, if it were in QMA1 to the U, then we could look at what is take the QMA1 protocol for the problem and look at what is Arthur's acceptance probability maximized over all possible quantum witnesses that could get sent by Merlin. Okay, and look at that as a function of theta, the angle by which the oracle rotates. Okay, so that's what I did. And what I showed was that function, which is sort of graphed in red here, has to be whatever it is. It has to be the maximum of finitely many real analytic functions. Okay, why is that? Well, it's because it can be represented as the largest eigenvalue of a finite Hermitian matrix, right? Where each entry of that matrix is a polynomial in sine of theta and cosine of theta, right? And so that, overall is the eigenvalues of such a Hermitian matrix are a bunch of analytic functions of theta, and then you're just taking the maximum, okay? But then if the protocol is a QMA1 protocol, then we know that when theta is 0, then you probably have to reject. When theta is anywhere between a half and 1, you must accept with certainty. Is this? Oh no, this doesn't work. So it has to look. It has to sort of flatline, after theta becomes more than a half. Okay, but then a maximum of finitely many real analytic functions just cannot do that. Okay, why can't it? Well, because if it's constant on any non-trivial interval, then it has to be constant everywhere, right? That's just undergrad real analysis. Okay, so that was the argument. Okay, but now, the question of how well can QMA protocols be amplified, let's say in the, including, in the real world, in the non-Oracle world, that question remained. And just last year, there was what I consider a blockbuster result from Stacy Jeffrey and Freek Witteveen. And, and really something that I had not expected to be true. Okay, or at least I would have had no idea how to prove. Okay, they showed that even in a black box way, any QMA protocol can be amplified to have completeness error 1 over doubly exponential in n. Okay, remember, the easy thing to do is 1 over exponential, right? So how do they do 1 over doubly exponential? Well, the basic idea is if you could just, give a protocol and then if Merlin could just describe to Arthur exactly what is the probability that his protocol should accept, then Arthur would be able to do exactly the right rotation through Hilbert space to get from, whatever was the angle that his is unamplified protocol ends up at, like all the way to accept with probability 1, right? So like the whole difficulty is just that the acceptance probability of the original protocol is some crazy real number, and Merlin can't describe that real number to Arthur. I mean, he can describe polynomially many bits of precision of it, but that's not good enough. That only gives you 1 over exponential error. Right, so their new idea was to describe the acceptance probability via the amplitudes in a quantum state. Okay, so they have Merlin also, in addition to the witness, they have him give Arthur this quantum state eta, which sort of encodes the acceptance probability P via an infinite, decreasing geometric series. Okay, and they showed that if you could provide this, like the entire infinite series, then you actually get a perfect completeness protocol. Okay, there's a way to measure this so that you accept the valid witness state with probability 1. Okay, in reality, you only have polynomially many qubits, which means that you need to cut off this state, after like exponentially many terms. But when you cut it off after exponentially many terms, then you're left with an error term that is only 1 over doubly exponential. Okay, so very clever. Okay, so then I wondered, okay, can I improve my 2009 Oracle separation to show that their result is optimal, right? Or maybe there's some better way that you can amplify QMA to have 1 over triply exponential, or 1 over Ackermann or Busy Beaver or whatever completeness error. Okay, no. In fact, we've been able to show that with all black box amplification procedures, this 1 over double exponential completeness error is the best that you can do. Okay, and this is where we use GPT-5 Pro to help. Okay, and here was the key lemma that we needed. Okay, it basically says, again, let E of theta be an n by n Hermitian matrix, each of whose entries is a degree D polynomial in cosine theta and sine theta. Suppose that the largest eigenvalue of E of 0 is small, so it's between 0 and a third, but suppose that whenever theta is between 1 minus epsilon and 1, then the largest eigenvalue of E of theta is large. I'm sorry, but so whenever theta is between 2/3 and 1, then the largest eigenvalue of E of theta is between 1 minus epsilon and 1. Okay, then epsilon has to be at least 1 over exponential in n times d. Okay, so it's sort of like a quantitative version of that real analysis thing that I did before. It says that not only can this maximum eigenvalue not flatline at the top, but it can only be sort of squashed down by so much and not more, right? Not to more than 1 over exp of n times d. Okay, and then a corollary of this, if you plug in that big N is exponentially large and little n, then you get that the completeness error of your black box QMA protocol has to be at least 1 over double exponential. Okay, so here was the lemma again, and now I can show you the proof idea. Okay, and the proof idea, I mean, like probably given a couple of weeks, I think that I could have proved this. Certainly, I could have proved it when I was younger. Okay. But in fact, the right thing to do turns out to just be to define some function of theta. Okay, one choice that works is f of theta is trace of I minus e of theta inverse. Okay, and why that? Well, because it has a very simple interpretation in terms of the set of eigenvalues of e of theta. Namely, it's just that sum there, if you think about it. This function was suggested by actually an earlier version of GPT-5. And now what's the point? Point is that this function, it is a rational function in cosine of theta and sine of theta of degree O of n times d. And we know that when theta is small, this thing can be at most, let's say, 3n/2. When theta is large, it has to be at least 1/epsilon. Um, just because we if we assume that the largest eigenvalue gets to like more than 1 minus epsilon, then then that's what happens there. Okay, and then we just solve, and we apply known results from approximation theory, and we get that n times d must be at least a log of 1/epsilon, and then we just solve for epsilon. Okay, I should mention that after I posted about this on my blog, and it got like this was not such a big deal, but it sort of it went semi-viral, I guess, just because this was one of the first examples of someone talking openly about here's how GPT-5 helped them solve a research problem, and then quickly a human mathematician, Philip Harris, realized that there's a simpler function that works. F of theta equals determinant of I minus E of theta. Okay, so again, the AI found a valid proof, but it was not the best proof. Okay, so my second little vignette involves the power of post-selection. Okay, and so it involves this complexity class that I defined when I was in grad school 23 years ago, called post-BQP. Okay, so basically, BQP is quantum polynomial time, right? Post-BQP is sort of quantum polynomial time where you get an additional ability. Okay, you get to, at some point, measure a qubit and then just condition on the event that the outcome of that measurement will be 1, even if that is exponentially unlikely. Okay, so I invented this class because I was thinking at the time about the anthropic principle and about the many worlds interpretation of quantum mechanics, and like what happens if you sort of guess a random solution to an NP complete problem, and then you kill yourself in all the branches of the wave function where you guessed wrong, and then you just sort of condition on the fact that you're alive. I don't recommend doing that, by the way. Okay, but I was interested in like how much computational power does that lead to if you combine it with quantum interference. And the result was kind of surprising. It's that you get exactly this very well-known classical complexity class, PP. So of course you can solve NP-complete problems, using post-selection. The surprise is that you can actually do a lot more than that. Okay, you effectively get enough power to solve counting problems as well. Okay, you can decide, like, given a Boolean formula, are the majority of the assignments satisfying or not, given this post-selection ability plus quantum computing. Okay, so that was the theorem that I proved, that these classes are actually equal. And that has since had a whole bunch of implications. We use it, for example, routinely in the analysis of quantum supremacy experiments, like the ones that Google has been, and others have been doing since 2019, or like boson sampling. Okay, we use, this sort of to argue about why these quantumly sampleable distributions are probably hard to sample classically. This also led to a completely new and different proof of the Beagle-Reingold-Spielman theorem from classical complexity theory, which says that PP is closed under intersection. Right, that was a big deal in like 1991, but post-BQP is trivially closed under intersection, and so once you know this equality, then Beagle-Reingold-Spielman just follows from it, right? Which is cool, right? Which is like I always like when we can do technology transfer from quantum complexity back to classical complexity. Okay, but so how did I prove this equality? Well, post-BQP contained in PP is pretty easy, at least if you define post-BQP the right way, so that the post-selection has to happen with at least 1/exponential probability. But then you really, if any of you know the proof that BQP is contained in PP, it's almost the same as that. right? It just you can just sort of write down the probability as a sum of squared absolute values of amplitudes, and you get an expression that just ends up being a PP expression. Okay, the more interesting direction is that PP is contained in post BQP. So here, let's say you're given a Boolean function f, and then we'll let s be its number of 1 inputs, and then our task in simulating PP is simply to decide whether s is greater than or equal to 2 to the n minus 1. Right? We want to know, like, are the majority of inputs 1 inputs or not? Okay, and the basic idea was that there is a simple quantum circuit, I've shown it here, that allows you to prepare as many 1-qubit states as you want, sort of each of which encodes S into the amplitude of the basis state 1. Right, so it's easy to make that state psi that I've shown there, which is like a superposition of 0 and 1, where the amount of 1 is proportional to S. Okay, with the appropriate normalization. So then you make a bunch of those states, and then what you do is now you really need the post-selection part, because now you manipulate these states, you measure them, you use post-selection in such a way that if S is greater than or equal to 2 to the n minus 1, then eventually you get a state that is sort of close to the plus state. If S is less than 2 to the n minus 1, then you never do. Okay, so the details of how that works won't concern us here. Okay, you can think of this as sort of a sort of transformed version of what Beagle, Reingold, and Spielman did using rational functions. Okay, but now I want to come to a question that Adam Boland, who was my former PhD student, is now a professor at Stanford, asked me a couple years ago. He asked, your old theorem of, PP contained in post BQP, does it relativize? And I'm like, well, of course it relativizes. I'm not doing any, arithmetization here, right? It's, certainly relative to any classical oracle A, PP to the A will be contained in post BQP to the A, right? My proof will easily show that. But then he said, no, I mean relative to any quantum oracle. And then I'm like, oh, I have to think about that. And that was much less obvious. Okay, so I thought about it for a bit. I was able to show, this was not trivial, that for every quantum oracle U that is closed under inverses or under complex conjugation, which means, if I give you access to the unitary U, then you can also query U inverse, or you can query U complex conjugate. If you have that ability, okay, then I can sort of prepare amplitudes that scale like the amplitude I'm interested in times its complex conjugate, which gives me the squared absolute value of my amplitude, which gives me a probability. And that's kind of the thing that I need in order to push through my original proof, right? But if you had an arbitrary quantum oracle, so one that you could only apply, let's say, in one direction, you just get to apply U, but you don't get to apply its inverse, right? Or you don't get to apply its complex conjugate. Then I was totally unsure whether my theorem relativized. Okay, and by the way, this was an issue that Greg Kuperberg and I noticed 20 years ago when we first proposed quantum oracles. Right, that there's an ambiguity. When I give you access to U, am I also giving you access to U inverse or controlled U or things like that? And we said, well, we're just kind of going to punt on that. Just make whatever choice seems appropriate to your problem. And and that's become a big issue recently in work by Ewan Tang and Mark Jandry and other people. Okay, so here again we see this issue rearing its head. Okay, so recent forthcoming work with Adam Boland and with Adam's student, Jordan Doctor, with Barak Neharan, and with GPT 5.5 Pro, we have been able to show that there exists an exponentially large diagonal unitary U. Okay, so even a diagonal unitary will work here. Okay, but crucially, you only get to apply it in one direction. It's not closed under inverses. It's not closed under complex conjugation. And relative to that U, PQP, which is the quantum version of PP, and which is equal to PP in the sort of unrelativized world, right? But I have to say PQP because it wouldn't even make sense to feed a quantum oracle to a classical complexity class, right? So PQP to the U is not contained in post BQP to the U. So in that sense, my post BQP equals PP theorem is not quantumly relativizing. Okay, here was the lemma that we needed in order to prove this. Okay, so basically, the part that I did, was to, or that we did, was to reduce the thing that we needed proved to a statement about sort of degrees of real polynomials. Okay, and so here, like this Z and W, you should think of as sort of the vector of diagonal entries in our diagonal oracle U, and then we can sort of build a quantum circuit that is sort of sensitive to the complex inner product between Z and W. Okay, but then the thing that we need is well, it's this, right? So so like we consider the Haar measure over all Z and W, where the inner product is some given A, okay? And then we look at the average of P over all of that, the average of Q over all of that, and we say suppose that like at the point a half, P is bigger than Q, but at the point negative a half, Q is P is P is large compared to Q, but at negative a half, P is small compared to Q. You should think of P over Q as a rational function that expresses the acceptance probability of a post-selected quantum algorithm. And then what I needed was that this quantum algorithm must make many queries to the oracle, which corresponds to these polynomials, P and Q, must have large degree, like degree linear in N. Okay, this question I gave to GPT-5 Pro, and after 40 minutes, it output a proof. The proof looked good to us. We went through it, and then later, Adam and Jordan realized that there was a step that GPT had asserted was obvious, which was not at all obvious. So I said, okay, so I'll ask it that step. And then it said, yes, you're absolutely right. It's not obvious. Let me give you a 5-page proof for that step. And it did it, and then that looked good to us. So, okay. So let me give you an example in progress. So I have work that I did with Sean Carroll, the physicist, and others 15 years ago, where we studied the rise and fall of coarse-grained entropy in two-dimensional lattice models of cream being stirred into coffee. And we are finally getting our act together to revise this paper now. So the models that we studied, like they involve sort of shearing. So we start with sort of half cream and half coffee in this 2D grid, right? The white pixels and black pixels, and then what we do is like we take like some let's say this is an n by n grid. We take n over 2 rows or columns of horizontally or vertically, sort of adjacent rows or adjacent columns, and we just sort of move them to the left or to the right with periodic boundary conditions. Right, it's just sort of going around the end if we reach the end, and so you can try this out, and it seems to stir. Right, and the question that really interests us was not the mixing. We say, okay, of course this will eventually mix, and we'll just get a close to uniform bitmap. We're interested in the approach to mixing. And we want to say that when you're sort of partially mixed, if you sort of coarse grain this image, if you look at, so just replace each pixel by the average of all the neighboring pixels, then you still get something that has many bits of Kolmogorov complexity, right? And so in that sense, like if we think of this coarse-grained entropy, it starts out nearly zero, and then it rises as we start mixing, and then once the system is fully mixed, then it just kind of looks like a uniform grayscale when you coarse grain, right? So then this thing should go back to zero, okay? Kind of like the physical universe, right? Starts very simple at the Big Bang, then, at the end, it will have maximum entropy, but not very interesting, just sort of a soup of photons. But in the middle, we get to sit in this nice conference room and have this talk. Okay, so okay, but there were various statements that we needed proved. One of them was that these shearing dynamics eventually do mix. Okay, so like that every state with an equal number of white and black pixels is reachable via these kinds of moves. GPT-5 Pro was able to prove that by just using results in group theory. And it reminds me of kind of the Rubik's Cube, right? Where like you want to show that like all the, what are all the possible states of Rubik's Cube that are reachable by just applying these kind of turning moves. Right, so it was able to apply standard group theory, which it knew, but I did not know, to prove that. Also, if you just do pure diffusion dynamics, so you just sort of repeatedly swap adjacent white and black pixels, we came to the realization that that is never going to produce any significant coarse-grained entropy. But in order to prove that, we needed like results from random walk theory, that we didn't know. GPT-5 was able to prove that. Okay, so let me discuss the general patterns here. Right now, AI seems to offer the maximum alpha, or, advantage at one, proving technical lemmas that would be standard for someone with different expertise than yours. Two, trying many possible counterexamples or many possible potential functions or other tasks that sort of require breadth-first search, sort of breadth over depth, as Timothy Gowers put it. Now I think that even if this were all that AI ever did, it would still have a big impact on TCS. Because, how often does it happen that we need to prove a lemma that is standard to some mathematician who knows stuff that we don't know? Right? That's a big part of it. Okay, so even if it was only that, but of course we should not feel confident that it stops there. Right? This is just what it can do now. So I'm going to end with a couple slides of what I'll call apocalyptic prognostications. This is like from this. If any of you saw this movie, the AI doc, they coined this term apocalyptimism. Okay, I think that the near future is going to be a golden age for solving open problems in TCS via human and AI collaboration, where it's better at some things and we are better at others. So we won't be cooked; we'll be cooking. Okay, so I guess my main advice to young people for the very near term would be get in on this while you can. Right? Now it's true that people with access to the most recent internal models will have a bit of an advantage, but that's probably short-lived. Like when I was at OpenAI and got to use the internal models, I got to live maybe 6 months in the future. Not more than that. Okay, I mean, will, AIs even be solving, P versus NP and our other greatest open problems? Well, I have no idea. That depends largely on how hard these problems really are. But I do think that at this point, that if our greatest problems are ever solved at all, it seems to me that AI is very likely to have played a role. Okay, now, it's possible that eventually we will not be able to do anything in TCS. Not only solving problems, but, coming up with new problems or new directions or whatever that AI will just cannot do better than us, right? I can't rule that out. On the other hand, if that happens, I expect that we'll have bigger things to worry about than the TCS job market. I think that will kind of be an issue for everyone on Earth. Okay, as how do we spend our time? Assuming that we get to live at all in that future. If you are worried about that, then my main advice would be, especially to young people here, would be to think about what can TCS do for AI alignment and safety. I think there are tons of opportunities right now to make a difference. So let me stop there. Thanks for listening.
Do we have any questions for Scott?
For the lemmas that you found GPT, that you found that GPT proved, were you able to find resources where similar lemmas have been proved in literature? And did you try to find those via ChatGPT itself and things like this?
Yeah, I mean, afterwards, like you can certainly find things in the literature, that were similar, right? And GPT will give you links to papers that, if you squint, with hindsight, you can see, yeah, this is kind of similar. Now it's funny, I talked before about my blog, right? When I posted, on my blog about how GPT had helped with this, one of the dominant reactions, was, well, this is just completely trivial. This is trivial linear algebra. So we're learning nothing about GPT being good at math. We're merely learning about Scott being terrible at math. So, I don't know, how to comment on that. All I can say is like, okay, I would have to give this lemma to, the audience here and see, how quickly people could do this without having seen the answer.
Any more questions?
Thanks, Scott.
Yeah.
So the results you showed were positive examples of where you actually found a proof, right?
Yes.
But presumably, this is a result of many other trials where you used GPT-5 Pro, but it did not give a result.
Mm-hmm.
Can you talk about like the patterns you're seeing and what it seems to help at and doesn't?
Yeah. So, I have asked it to, and I would say even 2 years ago, it was just full of hallucinations, right? It would just claim to have proved whatever, and often like doing the same thing that's familiar to us from like many, freshman exams that we may have graded, where, it just like, it looks like a proof and there's one step that is just sort of asserted to be obvious where everything falls apart. But now it's actually much better at admitting what it doesn't know. I've asked it to prove things I was interested in that were just too hard, and it admits it. It says, here's all the like easier related results that I can prove. So regarding where it seems to help, I mean, this was basically what I had to say about it. Yeah, it does seem to help the most, in sort of leveraging its sort of unbelievable breadth of knowledge, right? And in taking things that, yes, would have been standard to some human, but not only are you not that human, you don't even know which human that is.
Your advice for younger people is to get into the trend of using AI.
Well, that was one of my pieces of advice, yeah.
Yes. Related to that, you mentioned that there was one step in this long proof where after some time looking at it, you figured out it's not that obvious, and then it gave you a 5-page proof or something like that. I am a bit worried that if many young people start using AI too much now, they will lose the ability to detect these places. And isn't that something we should foster as well?
I absolutely share that worry. I mean, we could say, even before AI, like I was already getting more senile, I was farming out more and more like technical stuff to my students, right? AI just accelerates that process of senility for me. Right, but like for young people, they absolutely will need to have the skills, if nothing else, to tell when AI is lying to them. right? To be able to, work productively with AI, you have to be able to ask it the right questions, to push back on it, to know when it's wrong, and that involves sort of developing non-AI skills. I am very, very worried that those skills could atrophy, and I think that, we need to think about what can we do pedagogically to prevent that from happening.
Thank you.
All right. Thank you very much. I think we'll cut here questions to get to the next talk. Thank you, Scott.
Thanks.